All right, let's talk about one of the biggest, most stubborn mysteries in 20th century physics. For nearly half a century, a truly bizarre discovery had scientists completely stumped. Today, we're cracking open the Nobel Prize-winning theory that finally solved the puzzle, the BCS theory of superconductivity.
But let's start with a wild idea. Imagine you could flip a switch, and an electrical current would just flow forever without losing a single speck of energy to heat. It sounds like it breaks the laws of physics, right? But it's a real thing, a quantum state that drove scientists crazy for decades. And that thing is called superconductivity. It was first spotted way back in 1911, and it has these two properties that just seem, well, magical. Number one, electrons can move with absolutely zero resistance, and number two, it actively kicks magnetic fields out from its inside. That's called the Meissner effect. So you see, it's not just a perfect wire, it's something else entirely. And this is where our story really gets going. Because for the better part of 50 years, nobody, and I mean nobody, could figure out how any of this was even possible. It was a genuine quantum whodunit.
I mean, this timeline just says it all, doesn't it? It's discovered in 1911. Then, 22 years later, the Meissner effect pops up and makes things even weirder. It wasn't until 1950 that they got their first real clue, the isotope effect, which hinted that the vibrations of the atoms in the material were somehow involved. Just think about that, a nearly 50-year wait before Bardeen, Cooper, and Schrieffer finally blew the case wide open. So, what was this big breakthrough? Well, it all boiled down to a single, pretty radical idea about how electrons, of all things, could start working together. This is the absolute core of the BCS theory. And here's the central puzzle, the thing that seemed completely impossible. We all learn in school that electrons have a negative charge, so they should repel each other. It's like trying to push the same ends of two magnets together. It's a fundamental rule, but for superconductivity to happen, they had to be doing the exact opposite. They had to be pairing up. How on earth could that happen? The first piece of the puzzle came from Leon Cooper in 1956. He did the math and figured out that counterintuitively, even the tiniest, weakest possible attractive force between two electrons in a metal could be enough to bind them together. This was huge. It was the theoretical foothold they needed. Now, the only question was, where was this mystery attraction coming from?
The answer, it turns out, is found in this incredible hidden performance, a kind of unbreakable quantum dance happening inside the material.
Okay, here's a cool way to think about it. Imagine the grid of atoms in the metal is like a springy mattress. As one electron, our first answer, moves across it, its negative charge pulls on the positive atoms, creating a little dip in the mattress behind it. This dip is a temporary zone of positive charge. Now, a second electron moving nearby sees that positive dip and is attracted to it, effectively getting pulled into the wake of the first one. And just like that, you have a Cooper pair. The two electrons aren't directly stuck together, they're partners in this dance, linked by the ripple they create in the material. By pairing up, they start acting like a whole new type of particle, one that allows them and millions of other pairs to all fall into the exact same quantum state and move in perfect harmony. And this is a total game changer. You know, in a regular wire, the electrons are like a chaotic mosh pit. Everyone's bumping into each other and crashing into the walls, and all that chaos is what we call resistance. But in a superconductor, all these Cooper pairs lock in together. They form one giant, coherent quantum wave. They flow as a single unit, effortlessly moving around any obstacles. The result? Zero resistance. Now, having a beautiful explanation is one thing, but to be a truly great scientific theory, you have to make predictions that other scientists can go out and test. And let me tell you, BCS theory absolutely delivered. One of its biggest predictions was the existence of an energy gap. Because these Cooper pairs are locked in a stable partnership, it takes a specific amount of energy to break them apart and ruin the whole effect. You can think of this gap as a kind of protective force field that keeps the superconductivity safe. And here's the truly amazing part. BCS didn't just predict a gap. It predicted a precise, universal relationship between the size of that gap and the temperature where the material becomes superconducting. The magic number was 1.764, and when the experimentalists went to measure it, it was a perfect match. I mean, spot on. It was the smoking gun that proved the theory was right. And after that, the confirmations just kept coming. Remember that weird isotope effect from 1950? BCS explained it perfectly. Data on how the material absorbed heat, it matched. The theory even predicted brand new, mind-bending quantum effects that no one had seen before, and they were all confirmed. It was a complete and total triumph, and it rightfully earned the three of them the Nobel Prize in 1972. So why are we talking about this super abstract physics theory today? Well, because its principles are now the engine behind some of our most powerful and important technologies. You can literally draw a straight line from these principles to the world around us. That whole zero resistance thing, it's what allows us to build the insanely powerful magnets inside MRI machines and particle accelerators like the LHC. That weird Josephson effect, it's the key to making squids, the most sensitive magnetic field detectors on the planet. And the whole idea of a coherent quantum state is a foundational concept for building quantum computers. But, and in science, there's almost always a but, the story isn't quite over. BCS theory was perfect for that first batch of superconductors, which all had to be kept incredibly cold, just a few degrees above absolute zero. But then, in 1986, a whole new family of materials was discovered that could superconduct at much, much warmer temperatures. Here's the problem. That simple dance between electrons and the crystal lattice we talked about, it just doesn't seem to be strong enough to explain how these new high-temperature superconductors work. The original, beautiful BCS theory couldn't account for them. So, just as one case was closed, a new, even tougher one was opened. And that leaves us with a fascinating question for today. BCS theory was an absolute landmark of human intellect that solved a 50-year riddle. But the discovery of these newer, warmer superconductors tells us that nature is still holding some cards back. So, is the next great leap just an extension of BCS theory, or are we on the verge of a completely new revolution in physics, waiting for someone to crack the code all over again?